record button.
And I said such brilliant things too. Well, thanks, Donna. I'll just say, again, welcome everybody to the December, our Govys meeting or seminar. I'm really happy to have Doug Bates here as our speaker and his colleague, Jun Yan, who was going to be here helping and kind of in the background, I guess. I've heard Doug speak before and he's super interesting, and I know you're going to really enjoy this. So as usual, I let the speaker kind of introduce themselves as they go. So Doug's going to do that. You might have heard already that Doug's okay with asking questions as we go. So just put them in the chat or the Q&A, and I will interrupt Doug when I kind of see a chance or a good point to do so. So, all right, Doug, I'm going to pass it to you. I'll turn my camera off and I'll just be kind of tracking things. And thanks again for being here.
Well, thank you for the introduction, Wendy. Let me see. Can I share my screen? And I'm going to go to this screen. So does that give the
yeah, I can see it. It looks really
there?
good. Yeah, looks good.
Okay. As far as a bio goes, I'm going to introduce some of the bio and as part of the presentation, because what I want to talk about today is some history of open source software for data analysis, and in particular, how the R project came about, and some of the more recent approaches in open source software for data analysis, and how certain ideas from long ago have come back to have more recent currency in today's world. Sorry, let me see here. Okay, so anyway, we're going back to the 60s and 70s. So this is and the obligatory Grateful Dead reference in the song Truckin'. The refrain was about what a long, strange trip it's been. And it really has been. Oh, by the way, the URL at the bottom isn't quite right, but the first part of it is enough. So dmbates.corto.pub will get you to where the slides are available if you want to take a look at it. And one of the things there is mentioned in this point. Throughout, there's a lot of links, and often they're given to Wikipedia. In terms of technical topics and non-controversial topics, Wikipedia is a very good source of the background for some of the computing areas in particular. Oops, wrong one. I wanted to, there we are. So anyway, this is the R Govys group. And so, we're talking a lot about the R programming language. And it's been quite amazing to look back on the development of open source software tools, because it wasn't always clear that this path would be successful. And I think that it has been successful, much more than we could ever have imagined when we started off on it. So as I said, I'll primarily discuss the development of S, the language developed at Bell Labs, and then R, which when it was first developed, Rossi Haka, with his usual sense of humor, declared that it was a language that was not unlike S. And I'll try to put these developments in some context about what else was going on in the computing world during those times. So this is the bio part. I've been at it since the early 1970s, writing programming, and particularly programming for data analysis. And then at the time, everything was custom research programs. So you had to sit down. And in my case, I was working on nonlinear regression. And there wasn't nonlinear regression without having some kind of um, computing facility. So therefore, I was of necessity working with programming. I had a rather interesting background at the time in that the university where I was doing my graduate work, Queen's University in Kingston, Ontario, did not have an IBM mainframe. It had a Burroughs mainframe, and they used a different language. They used Burroughs extended alcohol. So it caused me to think about computing in a very different way. And then in the 1980s, I had the chance to work with the people at Bell Labs when I was on sabbatical. And so that was early on in the development of the language that became known as S. If you think you had an interesting introduction to learning programming languages, I went to Bell Labs and I was sat in front of a terminal, and John Chambers showed me how to log in, and he showed me how to start up this system, which at the time was called QPE, Quantitative Programming Environment, and then said, "I'm sure you'll do fine," and left. And so that was it. You get to learn the language by working with it right from the start. And just in case this is a note of a nostalgia for you, the most difficult part I had initially was distinguishing between one bracket and two brackets. I couldn't quite figure out what the two brackets were about. And then in the 1990s, we began to hear about some work that Rossi Hawk and Robert Gentleman were doing, developing this language that was not unlike S. And I started getting interested in that. And around about 1996, I was in Australia and New Zealand, got a chance to learn from those people. And by the time that our core was formed in 1997, I was involved in that. And so right through until 2023. As a result, I know base R pretty well. I'm not an expert on the tidyverse, and I had some experience with Python in the 1990s and early 2000, but it was for website development. It wasn't specifically for data analysis applications. For about the last decade, I've primarily been working with a language called Julia. And the reason that I bring this up is because I think it's not certainly something that everyone has to do, but it provides um, a different way of viewing things when you can have experience with different languages and learn how to work back and forth between those languages. So the early days, the 1960s and the 1970s, most computing was on mainframe computers. They would occupy entire rooms, and frequently a university would have a single computer. You know, you'd have the computing center, and most of the time that was an IBM System 360. And, you know, thinking back to those days, 360 was intended to indicate the 360 degrees an all-round computer, which was interesting when they wanted to come out with the next series. And so they called them 370, but it's not at all clear what the 370 was supposed to be about. One of the characteristics then was that the permanent data storage was limited to 9-track tape. And the a characteristic of the tape drives is that you couldn't do random access. You had to be running the tape sequentially, and you had to buffer the records in there. So that was restricting you to thinking about the sequential processing of the records. Um, most universities at that time, if you looked at what the computers were used for, it was most often batch-oriented statistical software. So BMDP was introduced in 1965, SPSS in 1968, and SAS in 1972. And these were the workhorses. Um, the hardware, the computing hardware, which was outrageously expensive, of course, came with the operating system and the compilers, and they used the languages COBOL, which is the common business-oriented language, and Fortran, which was formula translation, for COBOL for commercial applications, Fortran for scientific computing. Both of those dated back to the 1950s. IBM in the 1960s started to push a language that they were primarily involved in creating called PL1, which was Programming Language 1. They pushed it very hard, but not successfully. And this had many interesting effects because there's Fortran code around to this day. And, there's Fortran compilers. I forget what the latest ones were, what the latest version of the language is. Fortran, no, I can't remember, 17 or something like that. Uh, and you may wonder, it's not a wonderful language. Why is it still around? And it was because IBM was saying, no, 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 we'll stay with just COBOL and Fortran, and then we'll all migrate to PL1. And if you haven't been around for a long time, you may not have actually heard of it. One of the ways that this does come about for people in data analysis is that the initial versions of SAS were written in PL1, Fortran, and some IBM assembler. It got to the point in 1985 where SAS Institute kept trying to get people to write a PL1 compiler for uh, the microcomputers, mini computers that were being introduced around that time. And eventually they threw in the towel and they rewrote the whole system in C so that it could be ported to microcomputers. So I bring this up because some of the time the decisions that are made in areas that would seemingly be unrelated, like the programming language, can have profound effects in other areas.
Hey, John,
Yeah.
I'm sorry, I'm gonna interrupt. Can you go back to the other slide? Yeah. Somebody in the chat said, I guess it's Fortran 99.
Okay. Fortran 99 is the most recent version. Okay.
Yeah, and she said
Yeah.
they still use it, I guess where she works. The other
Oh,
thing,
yes.
yeah, the other thing I was going to mention was COBOL, because I hope I'm not just misremembering, but and I don't know how many years ago, maybe this was about 5 years ago or something, but I remember because I was working at the Bureau of Labor Statistics, and some states, I think it was the states, that some of their databases or whatever it was all, not the databases, but I guess the programs that they were using,
Yeah.
I think it was for the uninsured or something, was for or employment insurance was written in COBOL.
Yeah.
Anyway, the thing is that they were saying they were looking for people who could program in COBOL.
Exactly. Exactly. That was, the Y2K, the switching at year 2000, when you would need to use 4-digit years rather than 2-digit years. That involved a lot of people looking for COBOL programmers so they could update their software. And it became very lucrative for people, I think, especially in India, who knew COBOL, to be able to work on those Y2K updates.
Yeah, that's really
So
interesting. And I think just on one of your previous slides where you were talking about SPSS, that was written in 1968.
yeah, it was first released in 1968.
Wow.
I think that this is a link to Wikipedia.
Okay, and
Yeah.
I remember BMDP
Yep.
because I think I used that a little bit when I first started working for the Navy. Um, but yeah, I'm just a little bit shocked that SPSS has been around that long.
Yeah. Well, of those, BMDP and SPSS are no longer separate entities. And I decided to check how SAS Institute is doing. And you know, they're no longer so much in the data analysis as I would say commercial data processing area, but they're doing quite well. So BMDP and SPSS have sort of gone away. I think SPSS is now owned by IBM, but not really pushed that much. But SAS is still a very vibrant company.
Yeah, definitely. That's used still in the government. And I'll just put a little plug out here for, I'm pretty sure it still exists. There's an open source version of SPSS called PSPP,
Yes.
which which is kind of an interesting label or title for it. Anyway, thank you.
Well, thanks for bringing those points up. Um, so along the way, Bell Labs, AT&T Bell Labs, had quite an influence around this time as well. So this was in the 1970s and 1980s with the Unix operating system, and then the S language was created there. So they were coming out. The Unix operating system was first released in the early 1970s for mini computers, which was the DEC PDP-11 was one of the main ones. There were others, Control Data, Data General, and so forth. And then later hardware, which was called the DEC BAX 11 and some workstations. The VAX was from Virtual Address Extension. So this was one of the first affordable computers that could use virtual memory. And I think they were essentially 24 bits addresses as opposed to the PDP-11, which was 16-bit addresses. But I may be wrong about that. They also developed, as part of this work on the Unix operating system, C and C++ programming languages. And then S came along in 1976 and another version in 1980, which was a language for statistical computing and graphics. By the way, there's an interesting piece of history in there that the people who were working on the Unix operating system convinced the administrators to let them use a leftover mini computer on the basis that they would develop text processing software, which was used by the lawyers for repetitive documents that just had to change a few names and things like that. So before there was tech and LaTeX, there was something called TROF and DITROF and so forth. And so they used automating some of the legal functions as an excuse to get a computer from which they developed the software. And this Unix philosophy was often centered around software tools. The books by Brian Kernighan and his co-authors described this a lot. that the approach emphasized functions and pipelines or composabilities instead of an all-encompassing approach. Kernahan was very um, emphatic about, your programs should do one thing, or a function or a utility should do one thing, but do it well. And another thing that I remember about his books is that he would state and about loops that they should be able on occasion to do nothing gracefully. So he has very good aphorisms at the beginnings of his chapters. And actually, that was the beginning of my interest in software creation as a non-drudgery based art. um, so the original versions of S followed the philosophy that most of the code was a numerical methods library and a graphics library, and it was sort of glued together using many, many languages, RAT4 and M4 and so forth. And it had self-describing data objects in there. So in the mid-1980s, John Chambers started creating a new language, which was called Quantitative Programming Environment, or QPE at the time. And then around about, well, in that period, they decided that, well, they would just blend it in with the S language and create the new S language. And there was a project designed to provide a consistent approach to many different types of statistical models using classes and S3 methods that were implemented as attributes. And much of the work was done in the 1980s. This became a system for data analysis and graphics. And what set it apart was that it had self-describing data structures, including recursive structures. So if you go back to SPSS and SAS and such, they would have a data table, and it was a row-oriented data table because if you remember, it had to be on a 9-track tape and you had to read it sequentially. So you would read each record in, act on the record, and then go on to the next one. So all of your algorithms had to function as pipelines. In this case, their self-describing data structures could include recursive structures or lists. And that's the underlying basis of R to this day. The code was expressed as functions and function calls. And one of the things about the function call is that an argument to a function call can be the result of another function call. So this was a different way of composing the code. You didn't have to have a strict pipeline in there. And the code itself was a first-class object, so the functions could generate expressions in other functions. And that was very important to me because at that time I was still thinking about nonlinear models. And you had to describe the model itself, not as a formula or as a set of names. It had to be an expression that could be evaluated. So that would be passed in as an argument. So the code was itself could be passed around there. And the complexity in the S3 classes was achieved through attributes. The objects in S were in memory. All right. So the history of computing hardware, of course, is that every few years, Moore's law and all that, you end up with the ability to work on larger and larger objects in both memory and storing them on storage like solid state drives and so forth. So, we don't think anything these days of having terabytes, tens of terabytes, hundreds of terabytes of storage, and many gigabytes of memory. So these filter working in memory was very different in that way than working on the data as filtering through. You can do a lot with filters, but you can't do all the things that you can do when you're working in memory. And S was based on vectors, which could include things like factors and ordered factors. And a data frame was a named ordered collection of vectors. So this meant that when you were working in S, you were thinking of operations down columns. Operations down columns were more effective than operations across rows, whereas SAS, SPSS, many of the other, and a lot of transactional databases, the Oracle, PostgreSQL types of relational database management systems, they have a view of a relation or a table, but it's always in terms of row oriented. They want to do transactions. They want to insert, delete, modify rows across these tables. Whereas the columnar view of data tables is much better oriented toward the types of operations that we do when we're working on data analytic or data science points of view. The CSV format is another row-oriented format. And so this is something that I'm going to return to as we go along, because there's big differences, and the people in the database world are just starting, or I guess they're in the middle of a renaissance thinking of columnar views of data tables, when that's been what we've been doing in the R and S world for several decades now. And this idea of having memory in memory, many analysts felt that S could not succeed because it couldn't handle big data. And that's a very strange thing now, that we've gone from, I had a former student who, after she went off to work in a data science type of job, she was saying, well, S is okay if you want to do the graphics and all that, but you have to have SAS to be able to handle, large scale data. Strangely enough, the columnar point of view these days is better able to handle the data, large data sets. And I hope I can explain a little bit about why that's true.
Hey, Doug,
Yeah.
We had a question in the chat. Said, is that DuckDB? Is the DuckDB?
Yes. Yes.
Yeah.
Exactly. DuckDB storage formats like Arrow and Parquet and so forth. That's getting into the columnar data viewpoint.
Great.
So
Thank you.
outside of Bell Labs, at that time, the 1980s, and AT&T was a regulated monopoly because they had a monopoly on long distance telephone lines. So they could not also sell software, but they could share software for research purposes. So a small number of statistics departments were designated as beta test sites for S. And that meant that a couple of times a year, we'd receive a 9-track tape with the software and a couple of pages of instructions and their best wishes. So if you think that install the app is a big ask, try to take this from the tape and figure out how the hell to compile the damn thing. The commercial versions, porting S to Windows was the big deal. And that's because Windows, it was just too difficult to get the compilers and the whole compiler chain working. And there were still pieces of the software that were written in Fortran. And it's true for R today as well. So that trying to port things like that to Windows was very difficult. And that there were still many different versions of Unix. This was before Linux came along. And so many different versions of Unix on the workstations. So the people at the University of Washington Stats Department created and marketed a product called S Plus. The company was initially called StatsI. It went through many different um, incarnations, but that essentially it was out of University of Washington. And they licensed the base S code from Bell Labs, and they provided their own environment and packages. Here, and I want to look at the context of this in terms of things like personal computers in the late 70s and early 80s. The early microcomputers came along, the Apple II, the IBM PC, and at that time, they just didn't have the power to do things like compilation. So you still had to do the compilation on other computers and then move it in there. The Apple Macintosh also. Their potential was sufficient to cause, as I said, SAS Institute to rewrite their software in C. And then the Free Software Foundation was formed to promote free software, especially the Emacs editor. This seemed to me to be very strange. I was first introduced to the commercial version of Emacs, which was coming out of Carnegie Mellon. And then the free side, I learned about the free version of Emacs, and you naturally felt that it shouldn't be as powerful, and it turns out it was more powerful. And it was more powerful because of the ability to have many people working on it. So the Emacs editor and then the GNU system used licenses like the GNU General Public License. The Linux kernel was introduced in the early 1990s, and that caused a revolution in terms of the internet coming along at the same time. So you could, in those days, it was relatively easy to get addresses on the internet, especially at universities, and you could set up a web server using a Linux operating system, the Apache web server, MySQL, or another database system, and one of the languages, PHP or Perl or Python. So this became known as a LAMP bundle. And in combination with version control systems, you could then do distributed development and dissemination of software. So this was important in moving things to the point where you could have people at many different institutions working on the same software. We were working on the R project for 3 years before we ever got into the same room. Only a few of us had any firsthand contact with others. And the peculiar economics comes along there, and that setting up a web server wasn't terribly difficult. Some maintenance was required. The first copy of software was very expensive in terms of people time to produce, but the subsequent copies were essentially free, and the support could be crowdsourced. So it was a very different environment for developing software than at a commercial company where, at a commercial company, you needed to guard all of the software and the sources and have all the licenses and the support to people, personnel, and so on. Whereas in the free software world, hey, you just put it all out there and everybody could come around, take a look at it and contribute to it, and fix your mistakes and all sorts of good things in there. So In 1993, Rossi Haka and Robert Gentleman created a language that, as I said, was not unlike us. At the University of Auckland, there were still questions about how legitimate it was to copy the design of another language. So the design of the language itself followed that of S, but internally it was very different. It was much more influenced by scheme. And one of the differences was in memory allocation, in garbage collection. Any kind of an interactive language like this, the garbage collection becomes a really important part. S didn't do that. And interesting, the way that it got around it was it used memory mapping. How am I doing here? Oh, okay. So Martin Meckler started to make early contributions. Again, Martin was off at ETH in Zurich, Switzerland. I don't think he knew either Ross or Robert, but he convinced them to release the source code under the general public license. And those statisticians, especially those using S, began to contribute. And the mailing list, the source code repository, and R core were all created in 1997. We worked for the release of R version 1.0.0, which was released on February 29th, 2000. There's a story behind that. The date for a while did not exist on some calendars because if you don't know all the rules about leap years, you would think that 2000 wouldn't be a leap year because it's a century, but turns out millennia are leap years as well. And there, the major milestone was implementing S4 classes and methods. In terms of extensibility, the goal was to allow users to progress through many stages of use. You could start it off using it as a sophisticated calculator, then you could write scripts, then you could replace repeated operations with function definitions, and you could gather the functions and the data and the documentations into a package, and maybe then publish the package for use by others. CRAN and repositories like Bioconductor became clearinghouses for methodology, research, and so forth. And then the quality control and the consistency of the results. An interesting point along here was the use of literate programming. Initially, Frederick Leisch developed the SWeave system, then Yihui Zi developed the knitter system, and our studio now Posit developed Corto. So this was very important. The Jupyter notebooks, the name comes from Julia, Python, and R, were used to allow interactive evaluations and documents. So this whole ecosystem work built up around it. This is in contrast with the commercial model, where the software does not encourage extension by users. And Eric Raymond has a book about the free software movement in general called The Cathedral and the Bazaar. The best part is the title, because you can really imagine, the high priests in the cathedral dictating to everyone what was going to happen in terms of their data analysis, whereas R and systems like that are more like the bazaar. And the commercial software emphasized GUIs. There was a lot of attempts early on to come up with a graphical user interface for R, and there are some which people enjoy, but it's not nearly as central to the role because you're expected to sort of get in the spirit and roll your own analysis rather than depending upon what you can get through from clicks. One thing that's important here, that initially this company developing RStudio as an integrated development environment, they became very important in there. One of the things they did early on was hire Hadley Wickham, who was one of the really creative people in the R community, as their chief scientist. And so he was developing, and they support the Tidyverse family of packages, the Knitter and the Corto document preparation systems. And now they've gone to developing another multi-language data science IDE called Positron. So their name has changed to posit.co. And to many users, this is more central to R than is the base R coming out from R core. But it's a separate entity, it's a commercial enterprise, but it's complementary to and supportive of the R project. So it's sort of an ideal arrangement whereby the commercial company is providing support to those who want to have contracts and, all people to call to fix things. And then there's also the freewheeling and open source R project. So we have very powerful open source tools. I didn't mention in terms of POSIT. Part of the reason for the name change was that they're branching out from just supporting R to supporting R and Python and other environments. They're very widely used for data science. Julia has a smaller but dedicated following. What was I can't remember the name of the movie. Oh, it was in The Big Chill. I had a small but deeply disturbed following. So each language is supported by thousands of packages. Now there's 500,000 packages on pypy.org now, about 20,000 on CRAN and about 10,000 on the Julia registry. Surprisingly enough, even Microsoft supports open source through, they now own github.com. VS Code Positron is based upon Codium, which is the open source version, part of VS Code and other efforts. And the combinations of languages and packages provides incredible opportunities. If you look at what's going on in fields like AI and machine learning and so forth, there's enormous amounts of investment in open source software. But the problem is that there's so much to learn and remember. And the languages can be used in the read, eval, print loop through scripts and notebooks, in documentation systems like Corto, across many different platforms, from laptops to supercomputers, and in conjunction with version control systems like Git and Internet Repository. In the 1990s, this wasn't at all a sure thing that it was going to end up like that. But, our efforts on R were dismissed as freeware or the student edition. People didn't believe. And, it's not an unreasonable point of view that, a bunch of bearded professors at various universities would come up with something that could be comparable to the commercial software. There's reasons that the commercial software isn't as sophisticated a development environment as you might be led to believe. And the expensive commercial systems use proprietary formats and batch-oriented scripts and restrictive GUIs. So as I mentioned, this book, Cathedral and the Bazaar, contrasts these two approaches. The open source version I think, has been remarkably successful. And in that way, it has been a big boost to the overall data science area, in that you can experiment in the analysis algorithms without expecting that it was, you just have to wait around for the priests in the cathedral to implement a method before you can consider it as being legitimate. The bazaar is accessible. It's wonderful to have the different languages and systems with which to do data science, but it's confusing. And one of the things that you may end up with is that teams may need to use multiple languages. I think there's many environments in which you have your Python people and your R people, and they're not always on the same page. It's good to have exposure more than one way, but not everyone has the time or capacity to learn to use all of them. So in some ways, it's a matter of balancing the time to learn the tools versus time to spend using the tools. And in this sense, I'd like to mention, just in closing, this idea of some of the data interchange formats that we're using right now. In particular, someone asked about, is this DuckDB and Arrow and Parquet? These are names of formats, either for data on disk or for systems for doing data analysis and extraction. Arrow is an explicitly defined column-oriented format for in-memory tables, data tables, or external files. And the great part about it is that it allows for missing data. It can flag columns that don't have missing data. It allows for dictionary encoding. It is I would say it embodies almost all of the things that I can think of for working with data tables. And the memory image is similar, to the in-memory file representations, in-memory representations in pandas and polars and R and Julia. And one of the things about that is that you can keep an arrow file, and it can be read into Python or R or Julia or JavaScript, or, there's dozens of languages that can read the whole table. The files can be memory mapped because the file on disk is exactly the same representation as in memory for many of these systems. And this becomes incredibly valuable. And Junyan and I wrote a paper for Chance about taking a very large database and converting it from CSV to Arrow, and then being able to read it into many of the different files. The reason that I mentioned, or one of the things here that's very interesting, is that this idea of columnar data storage and memory mapping goes back to the initial S system way back in the early 1980s and on. So I think we got like 10 minutes left. Perhaps I can entertain some questions now.
Yeah, thank you, Doug. And yes, Doug put a plug in for the Chance magazine. Donna and I are co-editors. And I think your article just came out, right? It was published in the November issue. Hopefully I'm correct, which was published a little bit late. But anyway, Donna, we should make sure that that is open access. So we'll have to make a note of that and make sure that that is open. And then when I send out a link to the video to attendees, I'll put a a link to that article.
Okay.
Yeah, we have a couple questions. One in the chat. I gotta see if I can find it. But hopefully I'll say it by memory here. Oh yeah. Could you explain the R core's version control system during its development?
I'm sorry.
It said, could you explain the R core's version control system during its development? So I'm wondering if they're referring to things like
Well,
Git
we
or,
used, um,
but you didn't have that then, right?
well, yeah, we did have, Git wasn't available and certainly nothing like GitHub. And that's one of the differences for something like Julia. When Julia was being developed, it was already, it's already a GitHub repository. There's never any doubt. And packages were all GitHub repositories. For R, initially we used CVS or RCS. I can't remember. There was the concurrent version system and the revision control system. I think we started off with RCS and then switched later to CVS. And that was it worked by using remote shells and remote execution. And so the point on that was that you had to have a login, and in some ways that was my greatest contribution to our core, because I had a very good working relationship with the people who administered our computers, and I convinced them to allow me to create my own systems and have logins for the other people in the R core team. At one point, I guess it was after Robert Gentleman had left the University of Auckland and gone to Harvard, that the University of Auckland was seeing that people were using this R thing, and they thought, hey, maybe we can make some money off of this. And so Rossi Hawka put out an emergency. I've got to get this off of the University of Auckland computers. So for a while, that was all on the computers. And you mentioned PSPP. That was also on the computers. These were all computers that were in my office. If I accidentally knocked over swirled around in my chair and knocked over the computers, I could take all of the open source software in the planet down with me. And I think, I believe, interestingly, these days, R is the only popular language like this that is not housed on GitHub. Python, the main repository for Python is on GitHub, Rust and many other languages are there, Julia certainly. But R continues to be on some servers at ETH, which partially has to do with not liking Microsoft.
Yeah, okay. I find that pretty interesting, but I won't, there's other questions in the Q&A, so I won't delve into why I find that interesting. Um, so the first question, thanks for the excellent presentation. I agree, it was wonderful. Is technical debt as a problem more restricted to commercial software than open source software? I guess technical debt is the cost incurred from decisions that speed it up or hardware development. Yet those same decisions are detrimental in the long term, like bug fixes and code refactoring.
Hmm. I, I don't know. I've never really been involved with commercial software development. I've always been in this open source world. So I guess I can't really compare the approaches.
Yeah, for what it's worth, I often thought that the one of the many positive things, in my opinion, about R is that uh, there's the rapid development through packages and, people doing research, and they provide packages that implement the research and the new methodologies, which are slow to come to commercial software if they ever do. And it makes sense, I guess, because with the commercial software, they have to make sure it works. There's maybe a lot of development cost in that. And I guess maybe, changes can be expensive. So uh, maybe that's what's in part being referred to here. But okay, we have another question. For AI use cases, which language would you say is stronger now, Python or R? A lot is being developed in R lately. What do you think about that?
Um, I don't really know.
Mm.
uh, been retired for 10 years now, and I've just decided that I don't have the strength to keep up with and the energy to keep up with AI developments. Sebastian Raschke, who's at my department, um, he's he's an educator in AI, and he's been very active in PyTorch. So that's what I tend to think of in the AI world. Is I know that companies like Facebook, Google, um, Amazon have devoted enormous resources, and I believe that most of them are in Python-based systems rather than R. Um, I, Python is very good at developing glue code. Python allows you to pick pieces from different libraries and latch them together very easily. The internal organization of R is amazingly effective for its simplicity. There's like this internal structure called a symbolic expression, or sexprec. And I don't know, there's 19, 20, 21 types of them. But essentially, they're C structs that have certain fields, and they're um, you're, you're able to uh, use different flavors of them with different fields. Um, but that means that when you're communicating between R and a compiled language, you have to use the compiled language to understand the R structures that are being passed to it, and to take the results and package them back into a form that's accessible by R. So when you're doing the translation, uh, the the part that has to do the most work is the compiled part. Um, Python and Julia are a bit different in that they're able to do more of the data marshaling at the level of the interpreted code and then send it off to the compiled code. So for that reason, I would expect that a lot of the development would continue to be in the Python world. I mean, there's things about Python that drive me crazy. The fact that you don't have an array structure uh, is sort of, what do you mean you don't have an array? But
Yeah, that would, I don't know Python in any kind of detail, but yes, if it doesn't have an array structure, that would drive me crazy.
yeah, well, you have array structures, but that's what NumPy and things like that are about. So the fact that you have to add a package to get an array is kind of weird.
That is. Okay, next question. I was wondering where you use Julia in personal projects, production, etc. I'm a fan, but don't use it too much because I know most people aren't familiar with it. And I also heard too at some of our interagency R group meetings, hopefully I'm saying this right, that Julia, the use of Julia might not be suitable for, say, government agencies because there's not, I guess, an enterprise version of it, or it's not useful
Mm.
at an enterprise level, if I'm saying.
Hmm. Um, well, I will fall back on the fact that I've been retired for 10 years. So pretty much everything that I do is a hobby these days. And I'm interested in algorithm development, and it's a language with greater flexibility. Um, so, I can create algorithms that would be very difficult to create in R
Yeah,
or
and maybe, maybe if there is more demand, I'm not a Julia user either, so maybe once, if there is a demand for it at, sort of enterprise levels, if that is an issue, if I'm remembering correctly, then,
well,
then things change and, developments happen, innovation happens, so.
I think the greater impediment to widespread adoption is the fact that languages like R and Python are already available, and many people know them and can use them. And it's it's an investment. It's an investment in time. It's an investment um, in energy to learn this. So you have to have a good reason for it. My reason was that it's a richer language than R and Python, and therefore, and it was designed from the ground up for technical computing. The people who designed it are very experienced in many, many different languages, and it was able to use a lot of tools. So it's based upon a project that was called the Low-Level Virtual Machine, um, which came out of Argonne National Laboratories to take a language that looks like R and compile it down to machine code. So that's and that means that a Julia package, if you look at most Julia packages, they're 100% written in Julia. And, I was at the point where trying to work on mixed effects models in R, I was trying to step over this divide between the compiled language C++ and R. And that's, well, I'm glad I don't have to do that anymore. I didn't find that fun.
Well, you are motivating me to learn Julia.
We're insidious. It's like the days when I was convincing
Well,
people to
no,
learn.
I think I was going to ask you this question as a final question, but I think you've already kind of answered it. And here, but I'll ask it anyway. Oftentimes I get or encounter this decision that people, offices, agencies, what have you, make, which is, do we use R or do we use Python? And
Mhm.
it's as if, okay, we can only do one. We're not going to. So,
Yeah,
but my thought is, why do we only have to do one?
right.
Um, and so what are your thoughts about that?
Well, that was part of what I was trying to get at when I was
Yeah,
talking about the data storage formats.
exactly.
Um, and what Jen and I were showing in the paper for Chance is that you can take a CSV file, which is fairly large. I forget the number of records, number of variables, but um, it's like a couple 100,000 records and 30 or 40 different variables on all of these different instances. And the CSV file, there are no clean CSV files. They've all got their own idiosyncrasies. And so if you're going to do it well, you have to go through multiple times trying to read the thing and figure out all the options that you have to use. In this case, there was like 12 or 13 different ways that people wrote down missing for the missing data, it's NA or N/A or capital N, capital A, or all that sort of stuff. So it's if you're going to do it well, that data cleaning operation is going to take you some time. And rather than just passing on the code and having the penalty of the overhead each time, we took it and wrote it into a format that then, if somebody wants to use Python, they can just grab that file and it comes in clean for them. Somebody's using R, it comes in clean for them. If somebody wants to use Julia, or they want to use, Polars or Pandas or any of these systems, it comes in clean for them. And that's important, because then your analysis and reporting forms are they're more accessible to whichever language the particular analyst wants to use on that. So I don't think it's necessary that everyone learns to speak R and to speak Python and to speak Julia, etc. Systems like Corto to allow you to provide the reporting facility from different languages, and systems like Arrow that allow you to access the data tables from any of these languages efficiently and in a direct way, so that you don't have to do the translation steps in between. I think that that's going to be very important, and allow people to work with whatever language they like. If you're at the graduate student level, I think that you should know at least two. Yeah.
Yeah, that's a really good point. I think that, because one of the things that I was always frustrated about when I had to use like C or C++ was, I just had the command line, no IDE or anything. And so I'd have to, the frustrations I always had was the data IO, was the
Yeah.
data going in correctly? Was it coming out correctly? Because if it wasn't going in the right way, then anything I did was
Mm.
suspect. And then just to try to write the stuff back out to see if my code was right. Well, what if I wasn't exporting it correctly? So yes. And not to mention, I think you mentioned sort of proprietary formats. If it was a specific formatted data file, your data was in some proprietary format, then you had to have that software to
Right.
read it.
Mm.
So yeah, I think, and when you think about it, for statisticians, data scientists, the data are the fundamental, that's at the foundation, right? And so if we
Yeah.
can't, we have to deal with that in a good way, principled way, to to get started and to go forward.
Right.
So, um, yeah, I'll just close with this. I remember I was taking a graduate class about 10 years ago when I was at BLS, and I had to use SAS when I'm not a SAS user. And the first thing was, okay, load up this thing, and I couldn't load it. I had no idea how to load the data into SAS, and so I was just stuck.
Yeah. Yeah.
All right, with that, thank you so much, Doug. This was fantastic. We had lots of great discussion in the chat, but then also lots of thank yous to you for an excellent presentation. I just loved hearing about the history and the future. So, all right. So thank you again, Doug. I'll send the link to you also when we post the video, so you'll have it.
Good.
And thank you. Here's some applause for you.
Thanks.
You're welcome.
It's a
All
pleasure.
right. You take care. Thanks, everybody.
Thanks, everybody.
All right.
Bye.
Bye.